Determining net volume and available space. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already mastered. In our previous lessons, we focused on what we call the additive principle. This is the method where we take the volumes of various different solids and add them together to find the total volume of a single, combined object. However, as we move into more complex applications, we will find that many real-world scenarios require a different perspective. Often, we aren't looking for the total combined mass, but rather the net volume or the available space. Think of net volume as the leftover space. It refers specifically to the remaining space inside a larger container or structure after certain parts of that space have been taken up or occupied by other objects. Because we are dealing with space being taken away by these internal objects, our mathematical strategy shifts. Instead of using addition, we will now utilize a subtractive approach to find our answer. Keep this shift in mind, as we will apply this logic to a practical example in the next few slides. Understanding the concept. Imagine you are standing in an empty room that is completely filled with air. If you were to bring in a large cupboard and a heavy cylindrical pillar and place them inside that room, you'll notice that the amount of air, the actual available space, has decreased, right? The objects are now taking up space that the air used to occupy. Because of this, if you want to find the volume of the air remaining in the room, you can't just stop after calculating the volume of the room itself. You have to account for those new objects. You must subtract the volume of the furniture and the volume of the pillar from the total volume of the room. This brings us to the fundamental formula you'll need to use for all these types of problems. To find the net volume, you take the total volume of the outer structure and subtract the sum of volumes of internal objects. Keep this formula in mind, as we are about to break down a step-by-step process to apply it. Now that we've established that we are moving from an additive approach to a subtractive one, let's try to visualize what this actually looks like in practice. Step-by-step process to calculate net volume. Now that we understand the concept of subtracting volumes to find the remaining space, let's walk through a systematic, step-by-step process you can follow every time you encounter these problems. This will ensure you don't miss any details. First, you need to identify the outer solid. Look at the problem and determine the shape of the main container or the larger structure. Is it a cuboid, a cylinder, or perhaps a sphere? Once you've identified the shape, write down all its given dimensions, like length, radius, or height. Second, calculate the total volume. Using the dimensions you just identified, apply the appropriate volume formula for that specific shape to find the total capacity of the outer structure. Third, identify the internal solids. Just like you did with the outer structure, look inside the container and list every object taking up space. Note down the shape and the dimensions for each of these internal objects. Fourth, calculate the occupied volume. This is where you find out how much space is being taken up. Calculate the volume of each internal object individually. If the problem mentions multiple objects, like the pillar and the crate in our upcoming example, you must add their volumes together to find the total combined occupied volume. Fifth, subtract to find the net volume. This is the final calculation where we apply the subtractive approach we discussed earlier. Take the total volume of the outer structure you found in Step 2 and subtract the total occupied volume you found in Step 4. Finally, and this is a very important step, verify your units. Before you even begin your calculations, always check that all your measurements are in the same unit. You don't want to accidentally subtract cubic centimeters from cubic meters. Ensure everything is consistent so your final answer is accurate. Now, let's put this entire process into practice with a real-world example. Real-world example, calculating airspace in a storage room. Please look at the problem presented here. We have a rectangular storage room with a length of 6 meters, a width of 4 meters, and a height of 3 meters. Occupying the space inside this room are two distinct objects. a cylindrical pillar with a radius of 0.5 meters and a height of 3 meters, and a rectangular wooden crate measuring 2 meters by 1 meter by 1 meter. Our objective is to determine the volume of the air remaining in the room. For all calculations involving the pillar, please use 3.14 for pi. To solve this, we will follow the systematic process we just reviewed. Step 1 is to calculate the total volume of the outer structure, which in this case is the room itself. Since the room is a cuboid, we use the standard formula. Volume of the room equals length times width times height. By substituting our known dimensions, we calculate 6 meters times 4 meters times 3 meters, which results in a total volume of 72 cubic meters. Now that we have established the theoretical concept of the subtractive approach, let us apply it to a practical, real-world scenario. Now, in the following slides, we will calculate the volumes of the pillar and the crate individually so that we can proceed to the final subtraction. Real-world example continued. Let's move on to step 2, where we calculate the volume of the cylindrical pillar. As we can see from the problem description, the pillar is a cylinder. To find its volume, we use the formula, pi times the radius squared multiplied by the height. Plugging in our values, we have pi, which we are using as 3.14 times the radius of 0.5 meters squared multiplied by the height of 3 meters. First, we square the radius, which gives us 0.25. Then, multiplying 3.14 by 0.25, and then by 3, we get a volume of 2.355 cubic meters for the pillar. Next, let's look at step 3, where we calculate the volume of the wooden crate. This crate is a cuboid, so we use the standard formula, length times width times height. Using the dimensions provided, we multiply 2 meters by 1 meter by 1 meter, which gives us a volume of exactly 2 cubic meters. Now that we have successfully calculated the total volume of the storage room in step 1, we need to find out how much space the objects inside are taking up. Keep these two values in mind, because in the next slide, we will combine them to find the total occupied volume before we can finally determine the remaining airspace. Real-world example continued. In step 4, we calculate the total occupied volume. To do this, we simply add the volume of the pillar to the volume of the crate. Looking at our previous calculations, that is 2.355 cubic meters plus 2 cubic meters, which gives us a total occupied volume of 4.355 cubic meters. Moving on to step 5, we can finally find our net volume, which represents the available airspace we've been looking for. As we discussed in our fundamental formula earlier in the lesson, we take the total volume of the room and subtract the total occupied volume. So, we take 72 cubic meters and subtract 4.355 cubic meters. This leaves us with a final result of 67.645 cubic meters. Therefore, our final answer is that the volume of the air remaining in the room is 67.645 cubic meters. Now that we have calculated the individual volumes for both the cylindrical pillar and the wooden crate on the previous slide, we need to bring them together. Before we move on to look at some common pitfalls to avoid, let's quickly recap what we've achieved here by breaking down a complex space into simple, manageable parts. Common mistakes to avoid. Now that we have successfully worked through our practical example, I want to pause and discuss some common pitfalls. Even if you understand the subtractive principle we discussed earlier, these specific errors can easily lead to incorrect answers. First, let's talk about unit mismatch. This is perhaps the most frequent mistake I see. In our previous example, we were lucky because all our measurements were already in meters. However, in many exam questions, you might find the length of a room in meters, but the radius of a pillar in centimeters. If you perform your calculations without converting them to a single, consistent unit first, your final volume will be completely wrong. Always, and I mean always, check your units before you begin any calculations. Second, be careful not to confuse surface area with volume. It is easy to get overwhelmed by all the different formulas we have learned, but remember, when a question asks for available space, capacity, or net volume, we are strictly interested in the three-dimensional space occupied. Do not attempt to subtract the surface area of the internal objects from the total volume. That would be mathematically incorrect. Third, watch your order of subtraction. As we saw in the calculation for the storage room, we always take the total volume of the outer structure and subtract the volume of the internal objects. Mathematically, you must subtract the smaller internal volume from the larger outer volume. A negative volume simply cannot exist in the physical world, so if you end up with a negative number, you know you've made a mistake in your setup. Finally, do not ignore the number of objects mentioned in the problem. If a problem states there are 4 identical pillars, like the one we calculated in the example, you cannot just subtract the volume of one pillar. You must multiply the volume of that single pillar by 4 before subtracting it from the total volume of the container. Keep these points in mind as we move toward our final summary of today's lesson. Key takeaways. All right, we have reached the end of our lesson. Let's wrap everything up by reviewing the key takeaways from today's session on determining net volume. First, remember that net volume is simply the space that remains after we have accounted for all the internal objects occupying that space. It is the leftover space. Second, the mathematical process we use is fundamentally subtractive. As we saw in our step-by-step example with the storage room, the formula you should always keep in mind is net volume equals total volume minus occupied volume. Third, when you are faced with a complex, real-world problem that looks intimidating, the secret is to decompose it. This means breaking down that complex scenario into basic, recognizable geometric solids, such as cuboids or cylinders, so that you can apply the specific volume formulas you already know. Finally, always remember what your final answer represents. The result you calculate represents the available capacity or the volume of a medium, such as air or water, that is able to fill those remaining gaps. If you have mastered these points and avoided the common pitfalls we discussed earlier, you are well on your way to mastering volume calculations. Great job today!